Hi, everybody. This is a lecture on the Quine-McCluskey method. Um, if you, there's an initial lecture on this topic. If you, go to my YouTube account and subscribe, and then look at ENGR 596-27, you will see an initial discussion of the Quine-McCluskey method. And this is more details about it. What happened, the way that this became of interest is that problem 4 in test 18 asks you to find all minimal products of this function. And using the Carnot-Mapp method, it turned out to be a little bit tricky to do this. It's certainly entirely possible, but it's easy in this problem and in some of the others we've seen. It's easy if you use the Carnot-Mapp method to maybe miss one of the possible groupings. And of course, if you do this, then you're very likely to end up with the wrong answer. And so I happened to mention to some students that there was another way to do minimization called the Quine-McCluskey method. And so they were interested in seeing some more details about that. And I thought I would just make a short video for you showing you some of this. Let me tell you just a little bit about the Quine-McCluskey method, and then I'll proceed. The Quine-McCluskey method used to be regularly included in Electrical Engineering 235, but the decision was made to take it out. As you will see from this lecture video, ENGR 596-27, and also from what I will do here, the Quine-McCluskey method is more tedious than the Carnot-Mapp method, but it does have some advantages. First of all, the Carnot-Mapp method becomes really awkward if you have more than 4 independent variables, whereas with the Quine-McCluskey method, you can have as many independent variables as you wish. Also, I think another advantage, at least in my opinion, is I believe that it's harder to make mistakes with the Quine-McCluskey method. As I said, sometimes with the Carnot-Mapp method, you can overlook something, but that just, I think that's less likely to happen with Quine-McCluskey. So I just thought I'd let you see this, especially since some students requested it, and then you can make your own decision about what you like. So let's see how this goes. Now in class we have seen how, let's see. Actually, let me say, what happened in class on Friday, October 9th, and it's in the Zoom session, but we went over very quickly the notes for this ENGR 596-27, but we did that very quickly, and I don't recommend, I mean, if you're interested in this, I don't recommend that you go back and look at the Zoom session for October 9th. Instead, look at this video, ENGR 596-27. I think that will make more sense. And in that video, we saw how to do how to use the Quine-McCluskey method to find minimal sums for a problem where there were no don't care conditions. But our goal here is to see how to use the Quine-McCluskey method to solve this problem, and it differs from what's in this video in 2 ways. First of all, here, as I say, we want to find minimal products rather than minimal sums, and secondly, this problem has don't care conditions, and the one here does not. So what do we do? Well, what I'm going to do is I'm first going to show you how to use the Quine-McCluskey method to find minimal products without don't care conditions, and then finally we will see how to use the Quine-McCluskey method with don't care conditions to solve this problem that we want to solve. Okay, so first, like I say, first what we'll do is use the Quine-McCluskey method to find all minimal products of a function that does not have don't care conditions. And in fact, the one that we will look at is this. And we have actually done this problem already using Carnot maps, and that was in test 13. And we found that this problem, this function has two minimal products that are given right here. So how would we do this with the Quine-McCluskey method? Okay, now again, I'm going to, since you will have already seen that lecture 27 of ENGR 596, I will go rather quickly through this because so much of it is just the same as you have there. So as was the case in that problem, what you do first of all is to list all of your terms. And in this case, these are max terms because we're looking for minimal products, so you want to have max terms. So list the numbering for each one of those terms, 0, 2, 5, 6, 7, and so on. List all of these. And then we want to group the different max terms according to how many zeros they have. When they were min terms, as you saw in that lecture 27, you group them according to how many ones they have, but now when they're max terms, you group them according to how many zeros they have. And so looking at this list, the only term that has no zeros in it is 15, which is w prime or x prime or y prime or z prime. And then there are 3 that have only 1 zero, 7, 13, and 14. There are 3 that have 2 zeros, 5, 6, and 10. There are 2 that have 3 zeros, 2 and 8. And then finally, there's one term that has 4 zeros, and that 0, which is w or x or y or z. And so once you have grouped all of your terms in this way, which is, again, just like what we did in that lecture 27, except that there we were grouping, since we were grouping min terms, we grouped them by how many ones there were. And since these are max terms, we grouped them according to how many zeros there are. And now, just as we did before, we will look at consecutive groups to see if terms can be combined. Now you remember that when we were looking for possible combinations before, we looked at the numbers and we said, is the difference between the numbers a power of 2? That was one thing we checked. And also we checked to make sure that the lower number was larger than the higher number. Well, now we will still look for differences that are powers of 2, but now we want the lower number to be a smaller number than the higher number. As long as that's the case, then there's a possibility of combination. But if the lower number is a larger number, then there will certainly not be a combination. So 15 and 7, the lower number is smaller, so that's good. The difference is 8, which is a power of 2, and so those two will combine. And when you combine those two, you get x prime or y prime or 0. And we put 15 and 7 here to help us keep up with what two terms we combine to get that. And then we put a check mark by 15 and by 7 since we have used both of those in making a combination. 15 and 13 will also work because 13 is a smaller number than 15, and the difference between those is a power of 2. And when you combine 15 and 13, you get w prime or x prime or z prime. Now we don't need to put any additional check mark by 15, but we will put a check mark by 13. And 15 and 14 will work because the difference is 1, which is 2 to the 0th power. And when we combine 15 and 14, this is what we get. And there are no more possibilities. So this is the all the terms that we get that have no zeros in them. Okay, so now let's look at combining terms here that have 1 0 with terms that have 2 zeros. Okay, 7 and 5. 5 is indeed smaller than 7, so that's good. And the difference is 2, so those two will work. And when we combine them, we get W or X prime or Z prime. And then let's see, 7 already has a check mark by it, but then we'll put a check mark by 5. What about 7 and 6? Yes, the difference is 1, which is 2 to the 0th power, so we get 7 and 6 here. 7 and 10, we ruled that out for two reasons. The difference between 7 and 10 is 3, which is not a power of 2, and we can stop right there. That's good enough. But also the lower number is larger than the upper number, so that's another reason not to worry about that one. 13 and 5, the difference is 8, and so that will work. And when we combine them, we get X prime or Y or Z prime. 13 and 6, the difference is 7. That's not a power of 2, so don't worry about it. 13 and 10, the difference is 3, so that won't work. Then we go up here, 14 and 5, the difference is 9, so we don't worry about that. 14 and 6, the difference is 8, which is a power of 2, so 14 and 6 will work. And we put a check mark by 14 and a check mark by 6. And finally, 14 and 10 will also work, so we put a check mark by 14 and a check mark by 10. And you can see the terms that we get right here. Okay, now we look for combinations between terms in this group, the 2 zeros group and the 3 zeros group. Okay, and 5 and 2, the difference is 3, so that's no good. 5 and 8, the lower number is larger, so that's no good. 6 and 2, that will work, so we have 6 and 2 right here. 6 and 8, okay, here's a good example, 6 and 8. The difference is 2, but the lower number is larger than the upper number, and therefore this won't work. And you can see that. Look at 6. 6 is W or X prime or Y prime or Z, and 8 is W prime or X or Y or Z. So those two terms differ in 3 of the 4 variables, so we cannot combine them. Okay, what about 10 and 2? Yes, the difference is 8, and you can see what we get right there. And 10 and 8, the difference is 2, so that works, and we get this. And then finally, when we look for possible combinations between this group and the 4 zeros group, well, both will work here, 2 and 0 and 8 and 0. And let me remind you once again, each time you use one of these terms here, it is very important to put a check mark by it. Okay, so 2 and 0 will give us this term, W or X or Z. 8 or 0 will give us this term, X or Y or Z. And notice we've put check marks by 2, 8, and 0 here since we've used all of them. So in creating this middle column, we have actually used each one of these terms in the first column. Every single one of them got a check mark. Okay, so now let's do the same kind of thing to make still another column. Now, when you're combining terms now, it's a little harder to use the numbers. The way it would go, if you were trying to use numbers, it's like 15 and 7 and 7 and 5. Okay, the difference between the first numbers of the pairs is 8, and the difference between the second numbers of the pairs is 2. So these will definitely not work. The differences between the two pairs have to be the same. So let's see, 15 and 7 and 7 and 6 won't work. 15, okay, here's one, 15, 7 and 13, 5. You see the difference between 15 and 13 is 2. The difference between 7 and 5 is 2. And so that looks like a possibility, 15, 7 and 13, 5. And sure enough here, 15, 7, 13, 5 is right there. And you can see it, 15, 7 has X prime or Y prime or Z prime. 13, 5 has X prime or Y or Z prime. So they only differ in the Y variable. And when you combine them, you get X prime or Z prime. And you'll notice that if we had combined 15, 13, and 7, 5, we would get actually that same result. So we need to put checks by 15.7 and 13.5, but also by 15.13 and 7.5, because in both of those ways we will get x prime or z prime. Now 15.7 and 14.6 would give us x prime or y prime, but also 15.14 and 7.6 would give us x prime or y prime. So you just need to check, keep on going through this and check actually that's all of them we will have. But let me say that rather than looking at the numbers, I think that maybe the easiest way, once you get to the middle column, rather than trying to look at the numbers as I was just doing, I think it's easier maybe just to look at the variables. Like here we have x, y, z, so it won't combine with this one or this one. The first possibility is this 13.5, which has x, y, and z in it. And so then you look at the two and see that 15.7 and 13.5 only differ in the y variable. So that looks like these two are good to go. They will combine, as we've already noted. And then if you continued, again, 15.7, after you write down that one, 15.7, let's see, 14.6 would be another one right there, again, because x, y, z is here and they differ in only the z variable. And so that's why we get, when we combine 15.7 and 14.6, we get x prime or y prime. And then it certainly won't combine with 14.10. Then we look at 15.13, which is wxz. So the very first one down here, 7.5, looks like a possibility. And let's see, 15.13 and 7.5, that's right here. So that gives us a term we've already gotten, but still we need to put check marks there, as we've already said. And then anything else with wxz here? No other terms for wxz. And then when we get to 15.14 wxy, that there's one term here, there's a possibility, this 7.6, and it does work, but that gives us something we already have right here, 15.14 and 7.6. It gives us this x prime or y prime. So, but again, we'll put a check mark by 15.14 and a check mark by 7.6. Then we look at combinations between this group and this group, doing the same thing. And out of all these, there's 5 terms here and 3 terms here, but consider all the possible pairings there. So there'll be 5 times 3 or 15 possible pairings, and there's only 2 pairings that will work. 14.6 will work with 10.2, and 14.10 will work with 6.2. And both of those pairings give you y prime or z. So we'll put check marks by 14.6 and 10.2 and 14.10 and 6.2. And then finally, we look at pairings between this group, the 2 zeros group, and the 3 zeros group. And there are 2 pairings that work, 10.2 paired with 8.0 and 10.8 paired with 2.0, but both of those pairings give you the same thing, x or z. And if you look at it, we have actually used all of these terms here in the middle column. Now finally, when we get to this last column, you can see this has x and y in it, so it certainly can't combine with that. This has x and z, it can't combine with that. This has y and z, it can't combine with that, so we are done. There are no more combinations that we can make. And so now, and this shows you why the check marks are so important, now you have your prime implicates. Your prime implicates are simply all the terms that have no check marks. And the way we've done this, we've seen that everything in the first column has a check mark, everything in the second column has a check mark, but nothing in this last column has a check mark. So we have 4 prime implicates in this problem: x prime or y prime, x prime or z prime, y prime or z, and x or z. And beside each one, we put the numbers that are associated with it. So x prime or y prime is associated with 15.7, 14.6. We don't have to do this one as well, because all we're really interested in is the numbers. So 15.7, 14.6 for that one, 15.7, 13.5 for this one, and so on. We just list all the numbers in each case. We list those along the vertical axis of a table, and along the top horizontal axis of the table, we put all of the terms that are in the function. 0, all of the max terms, since this is a minimal products problem, 0, 2, 5, 6, 7, 8, 10, 13, 14, 15. So we put all of those numbers there along the top horizontal axis. And then for each row, we will check off the numbers in that prime implicate. So the first one has 15, 7, 14, 6. So in 6, 7, and 14, 15, we get X's. The second one has 15, 7, 13, 5. So in 5, 7, 13, and 15, we get X's. And so on like that. Now, once you have filled in that table with the X's, we're almost done. The way we reason is as follows. Remember, these are the prime implicates. How do we find out what are the essential prime implicates? They are the ones that are associated with X's that are alone in their columns. See, the fact that we only have one X in this first column tells you the only way we can account for max term 0 is by including X or Z. So X or Z is a prime implicate. Likewise, this X alone in column 5 tells us that the only way we can account for max term 5 is by including this prime implicate, X prime or Z prime. So X prime or Z prime is also an essential prime implicate. But now this X right here is also alone in its column, but that's also X prime or Z prime, so that doesn't give anything new. So we see that X prime or Z prime and X or Z are the two essential prime implicates. And so what you do then, and this is reminiscent of what we do with the Carnot map, we know that the essential prime implicates, of course, have to be included in every minimal product. And so what we're going to do is now usually if you were doing this yourself, you wouldn't have to draw the table again, but since I'm trying to teach this to you, I drew the table again. But then what I've done in this table is I have crossed out the row, both of the rows that contain the prime implicates, but I have also crossed out every column that corresponds to a column in which either of the prime implicates has an X. For instance, let's look down here at this bottom row. Okay, we've said X plus Z, X or Z is a prime implicate. In fact, is an essential prime implicate. So we're going to cross out that row. But notice that it had an X in column 1, so I cross out all of column 1. It's also had an X in column 2, so I cross out all of column 2. I'm sorry, let me say that again. I shouldn't be calling this column 1 and column 2. That's a little confusing. The first column is the column corresponding to max term 0. And since this essential prime implicate has 0 in it, I cross out all of that column, because by including that essential prime implicate, I've taken care of 0. Likewise, this has a 2 in it, so I will cross out the column corresponding to max term 2. It has 8 in it, so I've also crossed out the column corresponding to max term 8. And it has a 10 in it, so I've crossed out the column corresponding to max term 10. So that takes care of this essential prime implicate. But remember, this X prime or Z prime is also an essential prime implicate, and it has 5, 7, 13, and 15 in it. So I cross out columns 5, 7, 13, and 15. And I cross out also the row containing X prime or Z prime. Well, after crossing out all that stuff, you can see that there are only 4 X's that are left. We have the 2 X's in the 6 column and the 2 X's in the 14 column. So what that tells us is that X prime or Z prime ended with X or Z. That's what's essential. That alone takes care of all the max terms except for 6 and 14. But of course, we need to take care of that as well. But the interesting thing is that we can do so in two ways. Notice that if we included x prime or y prime, that would take care of both 6 and 14, or if we included y prime or z, that would take care of 6 and 14. So there's two equally good ways to take care of 6 and 14, and so there are two minimal products. In one of these we have x prime or y prime, and the other one we have y prime or z. And if you check, you will see that this is exactly the same result we obtained with the Quine-McCluskey method right up here. Okay, so now that we see how to do minimal products with the Quine-McCluskey method, now we're ready to do minimal products with don't care conditions. And really, there's not much different, but let me sketch for you how this will go. So now we get to the real goal, which was to use the Quine-McCluskey method to solve problem 4 of test 18. Now, we saw that for this problem, when we did it with the Quine-McCluskey method, we found these two minimal products. So how do we do this with the Quine-McCluskey method? Okay. Well, the first thing we do, and this was the first step with the Quine-McCluskey method as well, is this problem is written in terms of min terms, but we want minimal products, so we'll write it in terms of max terms. And this is what we got, and we talked about this already because, again, that was the first step with the Quine-McCluskey method as well. Now, once we have all of these terms, as usual, then we're going to list all of our terms so that we can group them according, and since we have max terms now, we'll group them according to the number of zeros they contain. And notice that we're going to throw in the don't care conditions along with the max terms. We initially will treat these all as though they're the same, just like you do in the Quine-McCluskey method. When you're determining your prime implicates, you treat all of these as the same. Okay. So you remember, it's only when you get to the essential prime implicates that you distinguish between the don't care conditions and the regular conditions. And we'll see exactly the same thing happens with Quine-McCluskey. But let's not get ahead of ourselves. So here are all of our terms. And as I said, we will group them according to the number of zeros that they have. So the no zeros group has only term 15. 1 0 has 14 and 11. Two zeros has 12, 5, and 3. 3 zeros has 8, 4, 2, and 1. And 4 zeros has 0. Okay, we can combine 15 and 14 to get this term, and 15 and 11 to get this term. 14 and 12 works. 14 and 5 does not work because the difference is 9. 14 and 3 does not work because the difference is 11. 11 and 12 doesn't work. And then here's another example. 11 and 12, the difference is 1, which is a power of 2. It's 2 to the 0th power. But the lower number is larger than the upper number, so it doesn't work. And if you compare, notice that these two things differ in x, and they differ in y, and they differ in z. So they certainly, since they differ in 3 variables, we can't combine them. So 11 and 12 doesn't work. But 11 and 5 does work. Excuse me, 11 and 5 doesn't work. The difference is 6. 11 and 3, where the difference is 8, does work. So we get that right there. And so far now, oh, and let's see, 14 and 12, well, we already said that one works, so we have that right there. So 14 got a check mark up here. Actually, 14 already had a check mark because of the 15 and 14. 11 has a check mark because of the 15 and 11. 15, certainly it's in both of these, so it gets a check mark. And then 14 and 12, we said that works, so 14 already has a check mark, then 12 will get one. 14 and 5, 14 and 3 don't work, 11 and 12 doesn't work, 11 and 5 doesn't work, but 11 and 3 does work. So 11 will get a check mark and 3 gets a check mark. And so we just continue on in this way, and it turns out that everything, again, just as was the case in the last problem, everything in the first column gets a check mark, and here are all of the combinations that we get. Now, at this point, though, it will be a little different from before, because remember, in the problem we just did, everything in the middle column got a check mark as well, but that won't happen here. For instance, 15 and 14, which has WXY in it, well, it can't combine with anything here, so it does not get a check mark. And there's not going to be any more chances for it to get a check mark. So that tells you right away this W prime or X prime or Y prime is going to be, since it's not getting a check mark, it's going to be one of the prime implicates. Likewise, this next term, W and Y and Z, it can't combine with anything here. So that's also the W prime or Y prime or Z prime is going to be a prime implicate. And this next one, W or X or Z, let's see. There is something that has a W and X and Z in it down here, but you can see that it differs in the W variable. This is W prime and this is W. This is X prime and X. This is Z and Z prime. So it differs in all three variables, so those won't combine. So 14 and 12, that doesn't combine with anything, and so it doesn't get a check mark. And likewise 11 and 3, which is X, Y, and Z. Let's see. Here is a term with X, Y, and Z, but again, X and X prime, Y prime and Y, Z prime and Z. So again, that also, these two differ in all three variables, and so they can't combine. So all four of our first terms here don't combine with anything, and so they are all prime implicates. But all the rest of these terms, fortunately, will combine, and you can see the combinations over here. For instance, 12 and 8 can combine with 4 and 0. 12 and 4 can combine with 8 and 0. 5 and 4 can combine with 1 and 0. 5 and 1 can combine with 4 and 0. 3 and 2 can combine with 1 and 0. And 3 and 1 combines with 2 and 0. So in making these pairings, all of these will get check marks. And so none of those is a prime implicate. And then finally now over here in this column, well, all of these columns are in the same group. And columns within a single group cannot combine with each other for sure. So there's no more possible combinations and we are done. So all of our prime implicates in this case are these four terms right here and these three terms right here. So as usual then, we will now list vertically all of the unchecked terms which correspond, here we go. Okay, we list vertically all of the unchecked terms, those correspond to the prime implicates. And you can see the first four are the four from up here. 1, 2, 3, 4, and then we also need to include these three terms. So you can see those included here on the vertical axis. But now is where we take into account the don't care conditions in the following way. Remember that the next step in the Quine-McCluskey method is to list along the top horizontal axis all of the max terms, but we do not include the don't care max terms, only the ones that must be included. So in other words, when we come up here, we do include 0, 2, 3, 8, 12, 14, but we do not include 1, 4, 5, 11, 15. So you can see this here, 0, 2, 3, 8, 12, 14. That's all that we include. Because remember, what this table does really, the first thing it does is it helps us to find the essential prime implicates, but it also helps us to check off to make sure that we've accounted for everything that must be accounted for. And that's these terms up here. These are the things that must be accounted for. We don't want to include anything up there that's a don't care condition, because don't cares don't have to be accounted for. So this is our table. And again, to look for, these are the prime implicates, but to look for the essential prime implicates, we look for X's that are alone in their columns, and you can immediately see here's an X alone in its column, so W or X will be an essential prime implicate. And here's another X alone in its column, so Y or Z will be another essential prime implicate. But there are no other X's that are alone in their columns. So again, as I did above, I will repeat this table. Here it says, W or X is essential, Y or Z is essential. I will copy the table and put it down again. And once again, what I'm going to do is I cross out the columns that have these essential prime implicates, the Y or Z. I didn't include the shading over here, but I don't think that's a big deal. You understand it should be shaded all the way over here. Actually, I guess for completeness sake, let me furnish that. So wait just a moment. So now we have that fixed. And notice that everything associated with this prime implicate, this essential prime implicate, everything associated with it, I've crossed with purple lines leaning to the left. So that row and the columns, this has 0, 4, 8, and 12 in it. So 0, now 4 is not listed up here. 8 and 12, all of those have the purple lines leaning to the left. And then our other essential prime implicate was W or X. It has 0, 1, 2, 3 in it. 0, 2, and 3 are up here, so they have to be shaded in. And here for this one, I've had green lines leaning to the right, so you see that. And 1 is not listed up there, but 0, 2, and 3 are. So in all three of those columns, I have green lines leaning to the left. And so after shading in everything, you can see that all that remains are these two X's here in column 14. So that tells us that the only term that has not been accounted for is max term 14, and it can be accounted for in two different ways, either by including W prime or X prime or Y prime, or W prime or X prime or Z. So we have two minimal products. Here's our two essential prime implicates, the W or X, which is on the bottom, W or X, and Y or Z right there. So as usual, the essential prime implicates have to be in every minimal product. And then, as I said just a moment ago, the two ways that we can account for that max term 14 are by including either W prime or X prime or Y prime, or W prime or X prime or Z. So that's what we have here, W prime or X prime or Y prime, W prime or X prime or Z. And if you compare these two minimal products with what we said above, these are exactly the two minimal products that we obtained in test 18 using the Quine-McCluskey method. So once again, this method is it's just another alternative, and I'm going to stress you don't have to learn this method. I think it's more tedious than the Quine-McCluskey method, but if you were trying to work a minimization problem with a large number of independent variables, you just can't use Quine-McCluskey. And also, this is easier to program. I think personally that is a little less error prone, but that may just be a matter of personal preference. But anyway, this was just in response to some student interest, and if you like it, great. It would give you a little enrichment and give you a way of checking your kernel map problems. But if you don't care for it, certainly don't worry about it. So good luck, and I'll see you all soon.